Electrostatic precipitators are one type of particle control technology. A small section of one is shown here on the left-hand side. There's two parallel plates with wires running vertically between them. Those wires are charged. They have a very strong, in this figure they show a very strong negative charge. The plates are oppositely charged, they're positive. The idea is that the dirty air or the flue gas or exhaust gas comes in from the back in this case, passes through the plates, past the wires, and particles become charged, negatively charged from the wires, and then migrate to the oppositely charged plates, and then collect on the plates, and then the gas coming out, the front end is clean, the particles have been removed. It also shows that the particles that have collected on the plates fall down into hoppers. Often they add wrappers or some kind of like hammer knocking device that hits the plates and knocks the particles off as they build up there. Now, if we look at a cross section, like down from the top, you can see that the gas is flowing left to right. We're looking right down in between the plates at these wires, and these wires or electrodes cause the particles to become negatively charged. I'll talk about that in a bit more detail. Because the particles are negatively charged, they then migrate to the oppositely charged or positively charged plates and collect there due to electrostatic attraction. Those wires create what's called a corona discharge, and this is a picture of what it would look like. It causes an avalanche of ions. There's a very strong voltage on it, and it kind of breaks apart some of the air molecules nearby and causes it to release electrons and ions, which then attach to the particles. We'll talk about that in more detail. We're going to draw an ESP, the two plates, in a slightly different orientation than what we saw on the previous slide. There are my two plates. I'm going to draw the charging wires. We'll have 3 of them running top to bottom. We're going to have our gas flow coming in left to right. So this is at some velocity v sub g. And then I'm going to draw the dimensions of these plates. We have height h, length L, and then we have a distance between the plate and the wire of d. So the whole channel has width 2d. Now again, the way this works is that we have these wires at very high voltage. We're going to zoom in now and look down from the top. That's the wire. And then here's the plate. And what happens is that this wire is at very high absolute voltage. And often it's around negative 50 kilovolts. And what this does is it creates an avalanche of electrons and ions which causes this corona, what we call the corona discharge. Or a visible glow. Now what's happening is that we have, let's say, these electrons from the air molecules have been broken up, and we also have this the plate on the other side here. So this plate might be positively charged or grounded, so it's oppositely charged or grounded, and then we end up with these electric field lines from the wire to the plate, which kind of have this shape. And so now you have these electrons on these field lines, and they are going to migrate toward the plate. Now, as this happens, we have the particles flowing through here. And so the electrons attach to and charge the particles. So let's say we have a particle that happens to be flowing through here. Maybe it's going from bottom to top, but this electron ends up crashing into it, and then it becomes negatively charged. Well, it's in this electric field, and so now the particle is going to migrate towards the plate also, following the electric field lines. So now we have our charged particles. That migrate toward the plates. Sometimes, especially in the winter time, if you have a balloon or something, you rub it against your hair, you notice it becomes electrostatically charged, and then it starts getting really dusty. It's attracting oppositely charged particles to it. So that's what is happening. Now these wires are so at such high voltage, they often end up sparking. So you'll end up seeing like 50 to 100 sparks per minute. And then again, these plates, the particles collect on the plates. Let's draw that. Different sizes. They'll build up, and then you have to smack the plates and knock them off. Now that's a general overview of how ESPs work. We want to be able to quantify their efficiency as a function of particle size. And so first we'll talk about what's called the drift velocity. And this is where if we do a force balance between the electrostatic force that is drawing that particle towards the oppositely charged plate, and then acting in the opposite direction is drag. And if we do that force balance, like we did a force balance on settling particles that were subject to gravity, we will get the drift velocity W of the particle. This is somewhat analogous to the terminal settling velocity due to gravity. Here's the velocity of the particle due to being in an electric field. And that velocity is W equals P times epsilon naught times E squared times D sub P times K sub C divided by 3 mu, where P is a constant of 1.5 to 2.4, and that is a function of the dielectric constant for the particle, and that depends on its material, what it's made of. And then epsilon naught is the permittivity of free space. This is a constant, and it's equal to 8.85 times 10 to the minus 12 coulombs per voltmeters And capital E is the electric field strength, which is in volts per meter. That if you are asked to solve for the drift velocity, it depends on particle size. So you would, that's the d sub p, and then if it's small enough, you'd need to consider the Cunningham slip correction coefficient k sub c. The other properties, though, the other values you would have to have or look up for p, epsilon naught as a constant. You would have to know capital E, the electric field strength in this particular ESP, and then mu is the viscosity. Now that we have the drift velocity, we can use it to analyze the efficiency or the collection efficiency of the ESP. The way to think about this is that the efficiency is equal to the distance traveled by the particle due to the electric field and its drift velocity divided by the distance, the full distance between the wire and the plate. So for example, let's say we have a wire and a plate that are so far x distance far apart, and if the particle is able to travel half that distance, then all those particles within, that kind of distance of the plate will be collected and removed before the gas leaves the ESP. And so we're going to analyze essentially the ESP channel from the wires to the plate. So it's kind of half of the entire width, just with D rather than 2D. And we can do this in two different ways. We can do it first by assuming laminar flow. Where this efficiency is equal to the drift velocity times the time that the particle spends in that channel divided by the width of the channel. And now we'll make some substitutions. We know that the time is equal to the velocity of the gas times, the travel time is equal to the length of the plates divided by the velocity of the gas. So we can make that substitution, and we get W times L over D times V sub G. And now we can make another substitution, knowing that the volume flow rate Q is equal to the velocity of the gas times the cross-sectional area, which is D times H. And so that means that V sub G is equal to Q over D times H. And we can make that substitution, and we get W times L divided by V sub G, WLH divided by Q. And then finally, we note that L times H is equal to the area of one plate. And so now the efficiency is equal to W times A divided by Q. That is for laminar flow, but what's more commonly used is an equation which assumes mixed flow. And in that case, the equation, it uses this W times A over Q, and has a special name. It's called the Deutsch-Anderson equation. And it is that the efficiency is equal to 1 minus the exponential of negative, typically it's written as A times W over Q. And remember, we're doing this, calculating this efficiency as a function of particle size, which does not directly appear in this equation. There's no d sub p in here, but it does appear in W, which again is the drift velocity, which is directly proportional to the particle size, the particle diameter. And so if we calculate efficiencies as a function of particle size, we end up with a curve. Let me draw some x-axis labels on here. So we have 0.1, 1 micron, and 10. Our efficiency, let's say we have 100%. You can achieve very high efficiencies with ESPs, such that your curve might look something like this. There might be a little dip there in the accumulation mode between 0.1 and 1. But otherwise, you can get close to 100% efficiency with these. And in terms of design, there's a lot of pluses to ESP. One is that you have a low pressure drop across it. There's no fabric resistance or filter resistance as you have with a filter. You don't have to have super high velocities to get good removal efficiency like you do with cyclones. You can get a high removal efficiency for most particle sizes. It can be greater than 99%. The minuses are that it costs you in electricity. It adds a non-negligible amount to the to our electric bills if we get our electricity from a coal-fired power plant that uses ESPs. You need a large amount of space. And then there's a high initial cost.